Okay, last lecture for chapter 16. Finally, we're going to look at some ionic solids and their solutions. And so we know that ionic solids, a lot of them are soluble and form aqueous solutions. And so if any of these listed here were aqueous, would they either produce a basic, acidic, or neutral solution? And so we have two sources of either an acid or a base. And so the cation can be a conjugate acid and act as an acid and make a solution acidic, and the anion can be a conjugate base and make a solution basic. And so we need to consider the source. Well, obviously the source is strontium chloride, but would strontium be the conjugate acid of what, right? So strontium, which has a +2, would actually be the source of strontium hydroxide. And strontium hydroxide, all soluble hydroxide, are strong bases. So it would be the source of a strong base, therefore wouldn't act as an acid. And so if a metal acts as an acid, it would also be considered a Lewis acid. And so the group 1, the alkaline metals and the alkaline earth metals, none of them are Lewis acidic, meaning none of them will react and receive a lone pair of electrons. And so we're talking about this group here and this group here, strontium. Those metals that are a better candidate to be Lewis acids are, the big one to remember is aluminum, are metals that are rather large, and that term is of course relevant, and have high charges. So better candidates is going to be the transition metals with higher charges, and then some of the main group metals, they can also be Lewis acids. And so back to, okay, flipping back and forth like crazy. What happened to my drawing? There it is. Okay, so once again, and then we also have to consider the chloride, right? So when you dissolve strontium chloride, you also get chloride, but chloride is not a conjugate base because it would have to react with water to form hydrochloric acid, and hydrochloric acid is also strong, so there's not going to be this reaction at all. The equilibrium would be way to the left, so this is going to be a neutral solution. Now ammonium fluoride, NH4 plus and fluoride minus, they both act as acids or bases, right? So ammonium is the conjugate acid of ammonia, NH3, and so it would be acidic. And fluoride is this would be the source or the conjugate base of hydrofluoric acid, and so it would be basic. And so then you would, I wouldn't ask you to tell me, you just need to say each ion is the source or will turn the solution acidic or basic. You have to look at the Kas and the Kbs, but I wouldn't go that far. This next one here is a little trickier, but you should recognize NO3 nitrate, and of course nitrate is neutral. NO3, which would be the conjugate base of nitric acid, and nitric acid of course is a strong acid, but this methyl ammonium here is the conjugate acid of methylamine. I'll draw it out. So this is methylamine. It has a lone pair. It can act as a Lewis base and react with water to make this ammonium salt, very similar to NH4. And so this would be an acidic solution, and because the nitrate doesn't act. This here, sodium, again, would be sodium hydroxide, would be the base, and so sodium is not an acid, a Lewis acid. Plus, we already talked about that alkaline metals are not. But this is formate here, CHO2, formic acid is the source. It would be basic, it would be a Lewis base. And then finally, bromide conjugate or the acid of that would be hydrogen bromide, and that's strong. So bromide is not going to react with water. So that is a reaction that does not occur. But aluminum, as I said, that's the big one. That's a Lewis acid. And so let's take a look at how it actually works. Just a summary for you. And here we have the reaction of aluminum. Aluminum will actually form an acid-base bond with the water around it. So if you take any aluminum salt that's soluble in solution, it will be surrounded in an octahedral fashion. It's large enough it can accommodate 6 water molecules, and it's the oxygen lone pair from water that actually donates a pair of electrons to an empty d orbital. There's 5 d orbitals, or a p orbital. There's 3 p orbitals, so there's plenty of p orbitals available that are Lewis acidic. So it's going to accommodate 6 of these water molecules. So those are in themselves Lewis acid, Lewis base interactions. But what will happen with one of them, one of these water molecules is actually going to donate the proton to a water molecule to form the hydronium ion, and then you are left with, if you wish, a hydroxide here. But so the charge does reduce because you are transferring an H plus to a water molecule, to a free-flowing water molecule, one that's not bound to aluminum, and so this is charged here. That's that ammonium ion, and you can measure that, and it will be acidic. But it's you need to use the Lewis acid, Lewis base type definition to determine that. Boric acid is one of my favorite examples. It acts just like aluminum with a lone pair. It's the p orbital, right? So if we draw it out, we are not actually loosening this bond, not until it takes up a 4th water molecule, right? So just to put this into contrast, if we look at sulfuric acid, it kind of has the same structural features, right? It's got OH bonds, so those are covalent bonds, and then this first one here is weakened and it kicks out the hydrogen, and that's what makes this acidic, right? That's not true here for boron. It's different. Boron has that lone pair, and we looked at that already in a previous lecture. It will actually bind to a water molecule in the same fashion that aluminum did. And once it's done that, then one of those OH bonds from a bound water is going to loosen and produce. But BOH3 is not going to donate a proton unless it is dissolved in water, and then it first forms a 4th bond. So it acts as a Lewis acid and not a Bronsted acid, as you might expect by just looking at the formula. Okay, so we also have polyprotic acids. We've looked at phosphoric acid. We're aware of sulfuric acid. So all that means is that it has several acidic hydrogens that can be donated. And lucky for us, and the non-complicated calculations means they come off one at a time, and each of them has its own Ka. The first one is always stronger than the second one. In the case of sulfuric acid, we don't have a Ka for the first one, so this first one comes off on its own. It's strong, and that also means that hydrogen sulfate is not a good, or it isn't a good conjugate base. It doesn't act as a conjugate base, whereas sulfate does. So the sulfate ion will actually act as a conjugate base, and that's because the second Ka here is weak. Again, you don't have to worry about recognizing them. You'll be given a table, and then just make sure that you use the right Ka if you're asked to use it in a formula. So here's an example. I'm not working it for you. I've got the solutions. We've worked enough ice tables, I think. The idea is the same. So ascorbic acid, which is vitamin C, actually has 2 acidic hydrogens. Here they are. I couldn't even tell you which one comes off first. Doesn't matter. We are given the Ka, and that's all that matters, and that's all we're going to worry about. If we have a 0.1 molar solution of ascorbic acid, then we know that it acts as an acid, and we end up with a conjugate base. The reaction is written here, and the math is still the same. It is products over reactants, so we have this expression here, hydronium ion times the ascorbate, maybe, concentration divided by the initial concentration of the acid, which is 0.1. Look, we make this go to 0 here. Solve for x, which is equal to the hydronium ion concentration. Need to do the test. So we take it divided by the original concentration times 100 gives me 2.8%. So it's a valid assumption. Don't have to work the quadratic equation, and then all I have to do is take the negative log to get the pH, and we are done. So we've done this excessively. Hopefully you know how to do that on your own at this point. And I just want to leave you with some critical thinking moments. So I don't know, maybe you've seen this commercial, maybe you haven't, but this actress is advertising Flow water, and she says it's alkaline water, it's good for you, it's healthy, and she drinks some of that alkaline water with a spritz of lemon. Okay, so what does alkaline mean? It means it's basic, and lemon has citric acid, which has 3 acidic protons, so this is basic. So you are risking neutralizing or turning this water into an acid depending on how much or what kind of a base is in there. Well, surely it's not going to be sodium hydroxide. Let's take a look at the label. And they love giving you obscured labels here, right? So they give you the analysis here, right? They tell you there's 32 parts per million of magnesium, 70. So those are all wonderful things. We want magnesium and calcium and so. But what is in here that makes this basic or alkaline? All right. So 2 things that are quite obvious. Sulfate, that would be the second conjugate base of the sulfuric acid, and that's definitely a conjugate base, so that would make it alkaline. Hydrogen carbonate, of course, there's a negative and -2. But also this interesting compound here, which is not a compound, but I'm assuming that NC3, this is a source of amine. Okay, so this is going to be similar, it's 3 R groups, lone pair. So there's some sort of amines in here, and amines are not necessarily healthy. Okay, so, but those are all sources that could make that basic. Now the question is, do we have acidic or basic water, and what is the point of having alkaline water in the first place? I'll leave you with those thoughts, and then when you're done thinking, let's work some problems and get ready for the exam. Good luck.